Hi there, today we got ourselves a MacBook Air. This one's a A1466, specifically 2017, so the board number is going to be 820000165. This one's in here because it's just not powering on. So the first thing we're going to do is I've already taken the back plate off of the MacBook. We're going to hook it up to our power supply and see what happens. I'm messing around with our camera settings right now, so every time I switch cameras, the screen will black out just because the cameras are turning themselves off when they're not in use and turning back on when I switch the scene. Something's going on with either OBS or it doesn't help that I have a computer with an Intel Core 2 Duo processor. That could very well be the issue. So we have our homemade DC power supply connected, and let's see what amperage we're consuming. We're consuming 0.107 amps or milliamps. So that's an interesting number. That is, it's getting power, but it's not properly turning up all the way. So easiest thing here is we're going to just open up our schematic and go down the power rails and see if there's a missing line. I'm just so happy that right now it doesn't look like it's a missing PM Sleep S4 the rail. So let's pull up our board view software created by Paul Daniels. And we want to look at the 820000165, which was the last one we worked on. So what we do is we just go over here to the PDF version of the schematics, and we're going to look up power aliases. Power aliases is on page 62 of our PDF. Here we are. So what we want to do is just check the power rails that are on the board and see what seems to be missing. So let's check and see if our PP bus is present. On a MacBook Air, that's typically around 8 volts. So let's switch this over to the overhead camera. Turn on our multimeter. And actually I already unplugged my power supply, so let's plug that back in and see what we get. Alright, so everything's connected. You know what I forgot to do? Let's see. PP bus is going to be this fuse right next to this coil. So that is, trying to do this to where you guys can see I don't have any that fancy multimeter software. So we're getting 8.6, so PP bus is present. Let's check and see what else are we missing. This is all different types of PP bus, so S5 high side computing ints. I don't think that's going to be any of the issues, so I'm just going to skip down and check and see if we have PP3V42_G3 hot. And let's see, what's a good spot that we can probe? Okay, right here, this is going to be our actual PP3V42 generator. So that I should be able to just poke without actually having to put it underneath the microscope. And we're getting 3.43. That's close enough to 3.42. So that is present. Now let's check and see if our S5, or before we do that, I'm sorry, let's check and see if PPVR TCG3 hot. This is going to be the 3.3 volt line that powers the real-time clock, is what RTC stands for. We need a clock in order for our computer to turn on, and it looks like I can't necessarily test that unless I were to get underneath the processor, or if I were to flip the board open, and I'm just kind of lazy right here because the board is actually still in its housing. So I'll pull it out here in just a second. Before we do anything, let me check and see if we have our PP5VS5. Is there a side on the board? Nope. Okay. I was hoping that we'd be able to cheat. What about at least PP3V3S5? Are you present on this side of the board? You are. Let's check and see if you're present. So it looks like we got a giant capacitor right behind the airport terminal. Yeah, we're getting 3.3. Ooh. Something is getting hot over here. So our Samsung chip on our SSD is getting hot. I'm just going to go ahead and quit being lazy. Let's pull the logic board out to get the rest of our measurements. Pretty sure that the SSD is going to require 3.3 volts in order for it to actually be recognized or for it to turn on. So it's probably just turning on at normal temperature. Let's see, let's organize all that. It's because you don't have the home button connected.
Yeah, but this is like... Oh no, I waited too long.
Hold on, there's a way around that. Okay, we're back. Alright, so we were just removing this board here. This one doesn't have any signs of liquid damage from the top. We'll check and see on the bottom side if there's anything that's pretty visible. But the customer doesn't remember spilling any water on it, which is a good sign. But let's just confirm if there actually is or isn't water damage. Things are finally starting to be a little normal here, so I can get back into a schedule of doing some videos. It's hard to find time to actually do the editing of the videos, but this live stream seems to be a lot easier. And who knows, if I can actually get into a regular habit of doing live streams, may invest and get a better streaming rig, because this one, as mentioned, it's only a Core 2 Duo. You're fine. Alright, so to the naked eye, there has been some sort of food or oil, some sort of substance right here. And looking at this part of the board, that's exactly what it looks like. It looks like someone may have spilled some food, so it's not quite liquid damage, but there is some corrosion. So, let's see if I can get that in focus right here. So we do have some corrosion here on the board. Come on, quit focusing. There we go. So we do have corrosion there, and like I said, it looks like there's some food here. So even though it's not necessarily liquid damage, this is going to be attributing to why this computer is not even turning on. So let's put our screen away. The thing with liquid damage is the tiniest little things can build up corrosion. Well, food's not necessarily so tiny, but just humidity. We lived in Charleston for a long time, and Charleston just naturally is hot, and it's so hot to the point that liquid sensor indicators, or LCIs, inside of iPhones and MacBooks would trip. So customers just aren't necessarily aware when their devices get liquid damage because it's hard to recall a time in particular. For instance, I'll call this customer and let them know, hey, it looks like we found some ramen inside of your food. Sorry, some ramen inside of your MacBook. And they'll probably be like, oh, yeah, that was from 6 months ago. I didn't think anything of it. Yep, that's why it's not working. Okay. So let's see. Apologize for that noise. Let me see what this looks like underneath our microscope camera. All right, so here we are. So that's probably our entire issue. Okay, let's see what is this. Let's go back to our schematic here. So this is our board view. This is the wrong orientation. That looks more familiar. Okay, so where we are is going to be right here. So Q8150 is where the corrosion's at. What does Q8150 control? Q8150 is going to be the MOSFET or transistor that sends our all-sys power good to our computer to turn on. So remember I said that we were getting 0.17. So by knowing that it was a higher number than what we've seen in the past, which is 0.02, this is actually getting signals to try to turn on, but you have to have PP3V3S5, PP5VS5 on, PP bus, of course. These signals have to be present. PP5VSO, PP3V3SO, these all have to be present before the MacBook will create a signal all-sys power good. All-sys power good then talks to the PCH, which is built into the processor, the CPU, and then the CPU will then send a signal, which creates our PM Sleep S5, PM Sleep S5, SR, S3, until essentially we go from a S5 state all the way to S0. S5 is going to be basically trickle voltage. It has power, but it's not actually turning on. S0 means computer's fully blown turn on. So we're missing, if I had to assume, we're missing our all-sys power good signal. Let's check and see if that is still present. So our components in question specifically are going to be R8153. You know what? Let's just replace those. We won't even test those. All this looks gross. Let's just replace all this and save some time. So we are going to need a donor board. Let me go grab one real fast. Okay, so this component's perfectly fine on our donor board, it appears. This whole circuit. So we're literally just going to replace all that stuff. Just to go ahead and kind of get this one quick and out the door, we'll just replace it. Yeah, all this just looks gross. In fact, the MOSFET looks like it might be fine, but just these two resistors and this capacitor, that just looks gross. I'm going to use my hot tweezers for this repair. And to cheat, I'll also... Oh, hold on. There we go. Okay, so what I was going to do to cheat is, for now, I'm going to use some heat at the same time. Oh yeah, that didn't take much, so that just came right off. And then you're gone. And you may be okay, but you look a little oxidized, so we're going to replace this. And that's gone. Now let's give this a nice cleaning. because I have a feeling that the oxidation from the corrosion was so much that where that one resistor was, we may have a missing pad. Let's find out. So everything might look a little darker since my last stream because I changed the Barlow lens that I had on the end of my microscope. I used to use a 0.7. That seems to be a very loved one, and I think I may just have a bad one. I don't know if it's the wrong size. I may have got shipped a Chinese knockoff, but I don't know anything about lens magnification. And the problem was I only had maybe 3-4 inches worth of working space. And that's okay with the iPhones, but when I'm doing MacBook repair, like trying to put the quick underneath to heat up an area, it's just very crammed. So I switched back over to my 0.5 Barlow lens, and I have a much larger view in my opinion, being able to zoom out this far and get in closer. My range is a lot larger. And with the 0.7, I was able to do a lot more iPhone work because I could actually zoom in further and do trace repair. But the difference between the workspace area itself of the 0.7 and the 0.5, or at least the 0.7 I have, wasn't really comfortable enough for me to justify, just losing all that space wasn't really worth being able to see that much more. In fact, I actually like being able to see a little or further out with the zooming completely out of the object zoom. And where am I going with this? Sorry. I like to be able to zoom out more while I'm working on the boards so that I can actually get a broader area whenever I'm just inspecting for general liquid damage. Alright, let's take this resistor. We really didn't need heat. Heat was probably overkill because the heat I use for heating up ground for like capacitors, I cheat a lot. I shouldn't say cheating, it's just a method I find that heats up the ambient temperature of the logic board so you can remove capacitors or anything that's soldered to ground a lot faster. Where'd we go? We're over here. But being that the resistors are on a line and they're not actually soldered to ground, then the heat from the quick was probably a little too much. And where'd we go? Alright, now is the capacitor. Now, capacitor is going to be soldered to ground on one side, so it is going to take a little longer for it to heat up. And what you can do to make it come off a little faster is you can apply some solder to both sides of the capacitor as you're heating up. Or, if you have access to a rework station, like a quick, just put it on some low temperature, so that way you heat up the ground area at the same time. And this is probably destroying my micro tweezer tip. I'll just replace it whenever this one fails. And I just lost my alcohol bottle. Alright, there we are. Okay, we'll fix that in a second. My alcohol's spilling everywhere back here. Another thing I really like about my 0.5 lens is I seem to be standing up straight more. And I have a chiropractor next door who's been picking on me, saying that I just have horrible posture. So I feel like this in the long run is going to help my neck, just so I don't have any geriatric issues in the future. But to each their own. Everyone has a different setup for their station. Okay. Let's see. Did that fix our issue? We have a fan spin, and our power supply is showing booting voltage. So that was it. Let's check and see what was going on here real fast. That was a really quick repair. I'm happy with this. So we didn't end up replacing the MOSFET. That wasn't the issue here. The issue was actually going to be more corresponding to R8156 and R8153 and C8159. So we have PP3V3S5 is going into R51, which is our SOP good C. P good C connection, maybe. I'm not too sure what exactly that is, but this looked really bad, which was our VMON QT base on one side, VMON 5V div, divider, I'm assuming, and then which was also connected to this capacitor right here, which was our VMON 5 div. So let's check and see what that is on our schematic, just to kind of understand what happened here. So, So R8153, where are you? All right. So I think I see what happened here. Looking at it, our PP5ESO, which is our turn on 5-volt rail, goes through a voltage divider right here. We know it's a voltage divider because we have two resistors with a ground on the end. So this is going to drop 5 volts to something lower. In fact, actually, it says right here, 5-volt divider, 1.7 volts. So this right here drops 5 volts to 1.7 volts. We have this capacitor, which if this was shorted, it's going to send the 1.7 volts or more to ground. That could have potentially been the issue, but what I think the issue here was R8153 is a 1 kilo ohm resistor, and it is 0.1, 0.2, a straight line that goes to VMON Q base, which tells our MOSFET here to, hey, we have all the signals, go ahead and turn on our all-sys power good to our CPU. I think what happened here was R8153 was just so corroded that it was gone. It was no longer resisting. This was a completely severed line cut right here. So our BJT version, or SO rail P-good, or Q8150 was getting VMON Q3 base, VMON Q4 base, and PP3VS5, but it was not getting our VMON Q2 base. So if all of these signals are present, we'll send our all-sys power good. If we follow all-sys power good, just here on the schematic, I'll show you. This goes CPU JTAG isolation. We're not too concerned about that. Here we go. It goes to this right here. It goes to a logic gate, U1950, and this is going to generate our PCH power OK generation, which then goes directly to the PCH stands for Platform Controller Hub. Here we are. So Platform Controller Hub, or Power Management, I'm assuming PM, Platform Controller Hub Power OK, which then tells the processor, hey, go ahead and turn on, send the rest of these signals, working computer. So there was a little bit of, I'm just going to call it some soup damage. There we go. I'm just going to go ahead and call it some soup damage. We're going to give this one an ultrasonic cleaning just to make sure there's no corrosion anywhere else. But I think ultimately that was it. That was the end of that repair. So if you watch this, I hope this has been enjoyable. I'm trying to do more of these. How long did this one take? Only 30 minutes. So that's probably one of the fastest ones we've done live stream in a good minute. So hope this has been enjoyable. I'll see you in the next one. Bye.